Okay, so good afternoon. Welcome back to the live tutorial sessions on mechanics and control of robotic manipulators. I am Isaac John, and we are into week 6 of discussing summaries of regarding the course, as well as discussing some of the relevant tutorial questions that is relevant to this week. So up till until now, we have covered all the topics up to dynamics of robotic manipulators, how to derive the equations of motions of robotic manipulators using Euler-Lagrange method as well as Newton-Euler method. We have also seen the differences between both of these approaches and when on which all situations either of these approaches could be more beneficial, and we have also solved a few examples regarding that. And this week, for week 6, we'll be mostly focusing on topics such as trajectory planning. So I hope you have been following the lectures of Professor Shantakumar Mohan. So unlike the previous weeks, here, in order for you to get a real feel of what is going on in trajectory planning, like it is also, I would highly recommend you to go through the MATLAB codes that is being shared during his lectures, that he is discussing during the lectures, because the theoretical knowledge can only take you so far, and with whatever he is discussing through the MATLAB codes, you will also get a real feel of how to plan trajectories for an entire manipulator. Because in the lectures we are only concerning the variables of we are only concerning with single variables, or rather a single joint variables, whereas in the MATLAB codes he is taking entire manipulators on a whole. So I cannot recommend enough that you go through the MATLAB codes, so that it will complement whatever you are learning through the theories. Okay, so moving on, we'll basically cover the summary of the topics that we have discussed or that we have seen in the lectures. Some relevant topics that will be helpful for you to solve tutorial questions. So we'll begin with the definition of trajectory. So what it says is that, like, during a robot's motion planning, the controller is provided with a steady stream of goal positions and velocities to track. So if you want to control a robot, like, most probably you will be given, in case of a 2-hour robot, you will be given an X and a Y position. You could maybe call it as a start position, and you would want your 2-hour robot, something like this, to go to some other position. Maybe if I label it as X goal, Y goal, let this be the goal position, and this be the start position. And you would want the robot manipulator to go from the start position all the way from here to the final position, which is labeled as goal position. And how you would go from the start position to goal position, and how would you plan the robot's motion from the start position to goal position, is what we deal with the trajectory planning. And you may see, it may seem that only the start and the goal positions are important in this case, but that is not the case. You are also required to track, most probably in most instances, you are also, in addition to positions, you are also asked to track velocities. So if you are given a 2 path, it not only the important thing is you have to track a path from a start position to the end position, but you'll also have to track in a given time how much distance you would be traversing. So velocities also mostly come into the picture. So in a sense, it says the specification of a robot's position as a function of time is called trajectory. So the final endpoints, the initial and the final endpoints, are not sufficient, but you will also require the motion of a robot from the initial position to the final position as a function of time, right? So this is where the positions and velocities, which is nothing but derivatives of positions and accelerations, comes into picture. So not only how you arrive at the goal position, but at what all time you would be arriving at specific points is also a matter of interest, right? So again, to emphasis on trajectory, the specification of a robot's position as a function of time is called a trajectory. If you are not concerning the time, if you are only interested with the robot's motion between final and an initial position, and you are not really worried about the time it takes to arrive, time it takes to traverse from a start position to the goal position, that is that is basically called a path of a road. It can have a path like this, it can also have a path like this, right? But with velocities, if the velocities are also specified, it cannot have infinite number of paths. It can only have a one path for a given specification of time. So we have also seen numerous methods to generate a trajectory for a variable from a start position to an end position, if you can recall the courses, right? So here, one more definition is there. The trajectory is defined as the time history of position, velocity, and acceleration of the end effector or actuator joints. So you can basically define the start and end positions of either the end effector in task space or the actuators in joint space. So for suppose if you are given a 2-hour robot, you have the task space as x and y variables. These are the task space. And you also have joint space variables such as theta1 and theta. And you can basically plan the trajectory in either the task space or in the joint space, right? Basically says it's the time history of position, velocity, and acceleration, right? So if you're planning in task space, you will have to give the accelerations of x and y coordinates, velocities of x and y coordinates, as well as positions of x and y coordinates as a function of time. Or if you're planning in joint space, you will have to give the accelerations of the joint space, velocities, as well as positions. These are all functions of time. So if a robot is at a given point, maybe give like in the example depicted here in this figure, it does not necessarily imply this to be in task space. This is a generic variable x0. So if a robot is at x0 at time t0, if you want to move the robot at position xf, if you want the variable x to be at xf at time t is equal to 0, we have something called a straight line interpolation, right? So we would want the variable to move in a straight line, starting from x0 at time t0 all the way to xf at time tf, right? So the basic straight line formula is given as this. So this is nothing but an equation of a line, right? We all know from our high school classes what the equation of line is. We have something like y minus y0 is y2 minus y1 minus x2 minus x1 times x minus x0 plus some intercept, what do you call it, some intercept c. So this would be equivalent to the slope of the line, and this would correspond to the change in x position. This would correspond to some intercept, and this would also basically, sorry, like if you are talking about this y, the y of time would be y minus y0 plus some initial time y0, right? This is nothing but an interpolation of, this is nothing but a straight line equation. But here in this context, the x coordinate would be the time in this axis, and the y coordinate corresponding to this straight line equation is nothing but the variable, the variation of the variable x, right? That is all this equation is. This is nothing but a straight line interpolation. This is one approach to plan the trajectory of a point starting from x0 all the way to xf. But what then if this is how we would plan the trajectory of the variable x, how would the velocities look like? So this is the profile of position. How would the profile of velocity look like? So the velocities x dot is nothing but the derivative of position, right? Dou by dou t of x of t, right? So this the position is a linear function of time. So if you if you take the derivative of position with respect to time, what would you get? You would get a constant velocity, right? Because if you derivate something of order 1 with respect to time, take the derivative of something of order with respect to time, you will get a constant. Velocity is constant, right? If you take the derivative of it. And if you further take the derivative of the velocity, how would the accelerations look like? If you take a derivative of something that is constant, so the derivative would essentially be zero, right? All the way, it'll be zero. This duration, the duration at which the velocity is constant, we'll have the accelerations as zero. But since there is a sudden increase in velocity, like the velocity basically increases, velocity at this instant from 0 to t0 is virtually zero. And at t0, it jumps up to this constant velocity. And between t0 and tf, it maintains a constant velocity. And at time t equal to tf, it suddenly jumps back to zero. This is how the velocity profile looks like. And essentially, acceleration would be zero between time t0 and tf. It'll be zero. But since there is a jump of velocity, a jump in velocity, an instantaneous jump in velocity at time t is t0, the acceleration would have an infinite instantaneous acceleration at time t is t0. Then suddenly it will drop all the way to zero. Then since the velocity is dropping instantaneously from time tf, from a constant to all the way to zero, our acceleration would also drop by an amount infinity at time t is t0, and it will again continue to be zero all the way. So this is the feature or peculiarity of a straight line interpolation, where you have acceleration that is theoretically infinite at these positions. So that is not desirable, right? If you are having some theoretically infinite accelerations at specific points, that wouldn't be you wouldn't want that on a robot for obvious reasons, because the motion of a robot would be very jerky, and it might not be good for the actuators also to have theoretically infinite accelerations at specific point of time. That is generally not preferred for, so that is why we generally don't go with straight line interpolation trajectory plan. Then we have covered in the subsequent sections, we have covered something called a cubic polynomial interpolation, where we use a cubic function. Like if x is the variable that we would want to control from a start position x0 at time t0 all the way to the time x, all the way to the final position xf at time tf, we would basically use a cubic interpolation polynomial. This is nothing but a cubic interpolation polynomial. Yeah, so a0 is a constant term, a0 plus a1 t minus t0 plus a2 t minus t0 square plus a3 t minus t0 cube. So if the start position, if the time at which if the initial position is time t is at 0, then the equation would look something like this. X of t would be a0 plus a1t plus a2t square plus a3t cube. Right. So here, how many variables do we have? We have a single coefficient, a constant coefficient a0. We have a1, we have a2, we have a3. So in order for us to solve these equations, we don't know, like we only know that our initial position is at time t, at time t is t0 is x0, and our final position is xf. right? We only have two equations, but we have four unknowns. We have A0, A1, A2, A3. So the advantage of a cubic interpolation is that we can also have velocity boundary conditions. So on top of position velocity, position boundary conditions, such as x0 and xf, we can also have velocity boundary conditions, right? So these are the boundary conditions. So when x at time t equals to t0 is x0, so corresponding to t0, we have x0. And we can also specify the velocity at time t equal to t0. So if our robot at an initial position has a velocity, we can also specify that as a boundary condition. This is the initial velocity. And at x, the position of x at time t equal to tf is xf. This is our goal position. And we also have a goal velocity. X dot tf is xf dot, right? So using all these three boundary conditions, we can basically formulate four equations. We can have four linear equations in four unknowns. With that, we can actually solve we can basically solve the coefficients A0, A1, A2, and A3. Right? So that is what we have depicted in this slide. So suppose for a simplified case, like will consider our velocities, our terminal velocities, our initial velocity and our final velocities to be zero. And the time at which we'll start our analysis is also zero, right? So it looks something like this. Our distance profile would look something like this. So our time starts from zero, and this is the time axis. And let this be the final time. And our distance profile would look something like this. It starts gradually and it reaches the time position, something like this. So this would be your xf, the final position. This is your x-axis, and this is your time axis. So your cubic interpolation function would look something like this. X of t would be a0 plus a1t plus a2t square plus a3t. And what are our boundary conditions? So x at time t equals to 0 is x0. So if you substitute time as 0 in this equation, what will you get? You will get it as a0, right? This would be nothing but a0, because at time t is 0, all these variables get cancelled, right? Then what is the second boundary condition? X dot of t is 0. So the initial velocity, we are considering it to be 0. So okay, so we'll also need one more equation. So I'll just drag it a bit further down. So if you take the derivative of this equation with respect to time, what will you get? X dot of t is nothing but a1 plus 2a2t plus 3a3t square. So this is the initial position boundary condition. So this is the initial velocity condition. So at x dot at time t equal to 0. So if you substitute t equal to 0 on this equation, what will you get? That is nothing but implies a1 is 0. And at the goal position, x of t is tf. What is your final position? So this would implies xf. The final position would be a0 plus a1 tf plus a2 tf square plus a3 tf cube, right? So now what will be the velocity? X dot at t is tf. This would imply xf dot, that is also 0 because our initial and final velocities are considered to be 0 over here. So our final velocities would be 0 is, if you substitute in this expression t as tf, you will get a1 plus 2a2 tf plus 3a3 tf square. So if you arrange or if you rearrange these equations into a matrix and a vector form, you will get something like this. You will get an equation, a system of equation like this, right? You will basically get a system of equation like this because the unknowns are A0, A1, A2, and A3. You already know what is this variable TF because this A matrix is only a function of TF. TF is the duration of your trajectory. So if it begins from T0 equal to 0 all the way to the TF, if the final position is achieved at time T is TF, that is basically known. And this vector over here corresponds to your boundary condition. This is your initial position. This is your initial velocity, that is 0. This is your final position, that is XF. This is your final velocity, that is also 0. So if you want to solve for this unknown, you only need to take the inverse of this matrix and you have to pre-multiply into this vector. So if this is matrix A and this is a vector X and this is a vector B, the vector X is nothing but A inverse B, right? So if you solve this equation, you will get the coefficient as this. If you solve this equation, if you take this A inverse and multiply this with B, you will get these equations, right? So your final trajectory would look something like this: x0 plus A1 is 0. Now A2 is 3xf by tf square minus 3x0 by tf square times t square plus minus 2xf by tf cube plus 2x0 by tf cube multiplied by t cube. This will be your x of t. Right? So corresponding to the time you give, for any time you give that is between 0 and tf, you will be able to correctly determine at what point each of these time corresponds to. So at what portion or at what point of this trajectory each of this time corresponds to, right? So that this is nothing but the equation of this cubic polynomial for, as a function of the time. So that is all it is there for the trajectory generation in cubic polynomial. Now, what else do we have? We know that the position profile of the cubic polynomial is something like this. It starts from the initial position. We consider it to be 0. So the position gradually increases as such. Then somewhere in the middle part, there is a point of inflection. Then as you can see, the rate at which the position changes is basically decreases. The rate is basically decreases. So initially the rate of position change is increasing, and somewhere in the middle it switches and you can see it to be increasing. So if you take the derivative of this curve, this is a third order polynomial, right? Cubic trajectory means it's a third order polynomial. If you take the derivative of it, you will get a parabolic curve that is nothing but a second order curve, right? So initially, as you can see, since the position is basically increasing with respect to time, the velocity should obviously be increasing with respect to time. And somewhere in the middle, you will have a point of inflection. That means the velocity does not increase anymore. It will saturate. The slope will be 0 at the middle. And from here to here, all the way from the midpoint all the way to the end point, you can see the position being decreasing. The rate of change of position is basically decreasing. That means the velocity is also decreasing. So again, if you take a further derivative of velocity with respect to time, this is a second order curve, right? If you further take a derivative, you will get the profile of acceleration. That is nothing but the first order curve. So at time t0, it will have a sudden acceleration, right? From 0, instantaneously, it will have some acceleration, right? And as you can see, it basically decreases. It is a constantly decreasing function from initial position all the way to the final position, right? Because as you can see, if you take as the slope of the velocity, you can see that it is constantly decreasing, right? The slope of the velocity is constantly decreasing with respect to time. So in that regard, we have a constantly decreasing acceleration profile. So this is very important. You have to analyze you have to understand how the profile of velocities, the profile of position, velocities, and acceleration would look like for a cubic trajectory. And we have also seen the case of the profiles for a straight line trajectory, right? We have seen how the acceleration would have infinite values at a specific point of time. So for the cubic trajectory, this is how the profiles of position, velocities, and acceleration would look like. Okay, so moving on, if you want to move the robot through via point. So if we have a start position x0, we have a goal position xd, and in between we have some other point called via point xv, right? So you can essentially plan a trajectory in two ways. So from x0 to via point, then from via point to the goal point, you can basically plan a cubic trajectory in two ways. So which are like when the velocities of via points are specified. So the initial position, so the velocities x0, x0 dot will always be specified, and the goal position and its velocities will also always be specified. But in case of via points, if we have via points in between, there are two approaches. In which case one is where the velocities of the via points are specified. That is one case. And in another case, the velocities of via points are not specified. So in either of the cases, we only have the location of the via point as a guarantee. In one case, we also specify the velocity of the via point. In another case, we don't specify the velocities of the via point. So if we are specifying the velocities of the via point, we can basically have two cubic polynomials, right, in between x0 and xv, that is one cubic polynomial interpolation. And between xv and xg, we can have a second cubic polynomial interpolation. It's just a repetition of what we have seen in the previous slides. But there are drawbacks actually. Like in case one, there may be discontinuities in joint acceleration across via point. So in case if we are specifying the velocities of the via point, if we are repeating the process twice, what we have described earlier, then there could be discontinuities in joint accelerations in via point. Whereas in case two, what we would do is that we would consider the final velocities and accelerations of the via point. So we have a segment, we have a first segment. So we consider the final velocities and acceleration of the first segment to be same as that of the initial velocities and acceleration of the next segment. So the final velocities and acceleration of the first segment is considered to be the initial velocities and accelerations of the second segment. So in that way, if you do that, you can have a continuous profile of acceleration. But if you specify the velocity of a via point, right, it could potentially lead to discontinuities in acceleration profile. It could have sudden jump from one acceleration all the way to another acceleration. That is the case because in case of a cubic polynomial, you can only have in boundary conditions for positions and velocities. Right? You can only control positions and velocities. And if you end up specifying a velocity for a via point, right, it could lead to some other different acceleration compared to a naturally occurring acceleration between the between x0 and xv. Because naturally occurring, we cannot control the acceleration. So naturally occurring acceleration would be something else, right? And due to the fact that you are specifying the velocity of the via point, the next acceleration would be something else. So there will be a jump from the that the final acceleration of the first profile and the initial acceleration of the second profile, there will be an instantaneous jump in this case. But if you're not specifying the velocity of the via point, right, there will be, if you're not specifying the velocity of the via point, then what we do is that we'll consider the initial acceleration and velocity of the second segment to be equal to that of the final velocities and acceleration of the first segment, right? That's all it is there. I would urge you to check the MATLAB codes that is being discussed in the classes, so that you will also get a real feel of what is going on in the background. If you plan a trajectory that goes through a via point using case one, what will happen? If you plan a trajectory that traverses through a via point based on case two, what is going to happen? You can actually see that in real time. Yeah, and these are the profiles of position, velocities, and acceleration. This is the profile of position. This is the profile of velocities. And this is the profile of acceleration. When the via point velocities are specified, right? So this is the initial time. This is the time at which you are supposed to reach at a via point. And this is the final time. So this is the initial position x0. This is the position that you are supposed to reach this is the via point, and this would be your goal point. And you can basically plan two polynomial trajectories between the first segment and between the second segment. It is nothing but a repetition of what we have seen in the previous section. And if you take a derivative of these two curves, you would end up, if you take the derivative of this profile, you will end up with something like this. This is corresponding to the first segment. This corresponds to the second segment. And as you can see, you have a discontinuity over here. And because of that, you will have a discontinuity in acceleration at this instant of time. At this instant, when time is via point, you will have a discontinuity in this acceleration profile. Because for the first trajectory, this is the naturally occurring naturally occurring accelerations. You have no control over these accelerations, right? And for the second profile, these are the naturally occurring accelerations, because you have no control over accelerations. You can only control the positions and velocities. And due to this, you can have a jump in accelerations. You can have a steep jump in accelerations. This is the case when the via point velocities are specified. Whereas if you take a look at the case where the via point velocities are not specified, you can see essentially like this would be your initial position, this will be your goal position, and this is your via point. And you can see how the velocities basically varies. So here the final velocities of the first segment, it's considered to be the initial velocities of the second profile or the second segment. So we can have a smooth flow of velocities in the velocity profile. And as a result, you won't get any discontinuities in acceleration, because it is already considered that when the velocities of the via points are not specified, the final acceleration of the first segment is considered to be the initial acceleration of the second segment. Okay, I guess I got the question from Perumal Sami. He says, why can't we change the basis from 1t square t cube to t? Okay, so you are essentially talking about a fourth order. If I'm not mistaken, you are basically talking about the fourth order polynomial. Maybe a0 plus a1t plus a2t square plus a3t cube plus a4 t raised to 4. I suppose this is what your question is, right? So normally we would only go with even odd numbered polynomials, odd degree of uh, polynomials of odd numbered degree. So that is either 3 or 5. Usually we won't go more than 5, because there is a reason to it. Because if you consider a third order polynomial, so I'll write somewhere here. Yeah, if you consider a third order polynomial, so I'll write it over here. Third order polynomial would look something like a0 plus a1t plus a2t square plus a3t cube. We have a fourth order polynomial, something like a0 plus a1t plus a2t square plus a3t cube plus a4t to the power 4. And a fifth order polynomial would look something like a0 plus a1t plus a2t square plus a3t cube plus a4t to the power 4 plus a5t to the power 5. So the reason we would only go with odd numbered uh, order of polynomial is due to the fact that we can only have odd number of, sorry, we have for an odd number of odd order polynomial, how many unknowns do we have? How many coefficients do we have? For a third order, we have a0, a1, a2, a3. So that in a way means we can control 4 boundary conditions, right? For a case of third order polynomial, we can consider the initial and final positions. We can also control initial and final velocities. But if you take a look at the fifth order polynomial, how many coefficients do we have? We have a0, a1, a2, a3, a4, and a5. We have 6 coefficients. So that in a way means we can control 6 boundary conditions, which are which are initial positions, velocities, and accelerations, as well as final position, velocity, and acceleration. But in case of a fourth order polynomial, we have 1, 2, 3, 4, 5. 5 boundary conditions that can be controlled. So that does not really add up. We can either control initial acceleration or we can either control final acceleration. But that does not make it complete, right? In order for it to be complete, we'll have to be able to control all positions, all velocities, or positions, all velocities, and all accelerations. So the number of equations that we can have from a fourth order polynomial would not suffice. So it's either third order polynomial if you don't wish to consider accelerations, we will do good with third order polynomial. If you want to have control over accelerations, if you want to have control over initial and final accelerations, we would go with a fifth order polynomial. That is why we would typically go with the odd ordered polynomial. Right. So I hope I have answered your question. Okay, so yeah, moving on. This is what we have. These are the profiles of positions, velocities, and accelerations when the via point velocities are not specified. Okay, so yeah, as we have seen in the previous slide, as we have discussed, we also have a higher order polynomial trajectory planning. So these 4 points exactly discusses the points that I have just mentioned or that I have just explained. Right, we'll go one by one. So it says for an n-actuated joint manipulator, the cubic joint space scheme is very efficient. So mostly we would limit ourselves within cubic joint space scheme or cubic trajectory planning. But as we have already seen, it can only satisfy at most 4 constraints. That is, it does not have any control over initial and final accelerations. So the 4 constraints are initial and final positions and initial and final velocities. Accelerations are not coming into picture. right? So if we desire to control the accelerations of initial and final positions or initial and final time, we can go for higher order polynomials. For example, what we have seen, the fifth order or quintic polynomial. So it has control over initial and final accelerations in addition to positions and velocities. But obviously, it will also require even more involved computation. So as you have seen earlier, in order for us to solve for the coefficients, we have to take an inverse of a 4 by 4 matrix, right? So in case of a quintic polynomial, a polynomial of fifth order, you will have to take an inverse of a 6 by 6 matrix. So the computations are a bit more involved, right? So the computations are a bit more involved. So again, like if you are interested, this is how a fifth order polynomial would look like. It has a constant of a0, a1 times t minus t0, a2 t minus t0 the whole square, a3 t minus t0 the whole cube, all the way to a term of order t minus t0 all the way to the 5. And the 6 boundary conditions we have: initial position, initial velocity, initial acceleration. We also have the final position, final velocity, and final acceleration. So if you substitute these values, initial time, initial, all these boundary conditions onto these equations, not only this equation, you will have to take the derivative of this equation to get the velocity equation. You will also have to take a derivative further to get the acceleration equations. And onto these 3 equations, you will have to substitute these boundary conditions. Then you will end up with a system of 6 linear equations in 6 unknowns, right? The 6 unknowns are A0, A1, A2, A3, A4, and A5. And basically, you can formulate a square matrix like this. This is how your linear system would look like. This is a matrix, this is an X matrix, this is a B matrix. And this X matrix is a vector of unknowns that you would want to find out. And if you want to find out the vector of unknowns, you only have to take the inverse of A matrix and pre-multiply it with the B vector. So this is a seriously involved process, but still it's only taking, if you can formulate this matrix, it is only a matter of taking an inverse of a 6 by 6 matrix. And again, this is how this is how basically the profiles would look like. So this is a fifth order polynomial starting from x0 all the way to xf. And as you can see, the velocity profile is a fifth order polynomial, right? And if you take the derivative, this will be a fourth order polynomial. So here you can see there is a point of inflection. So the velocity first increases all the way from here, then from this point of inflection, it basically decreases, right? And this is a fourth order polynomial. And similarly, you can see the acceleration to be a third order polynomial. So it first increases up to this point, right? The acceleration increases up to this point because this also has a point of inflection over here. So the acceleration first increases all the way to here, then it decreases to 0 at this position, and again it will further increase because we also have a point of inflection over here. It reaches the maximum negative acceleration, then from here onwards it decreases all the way to 0. So this is how the profile for a quintic polynomial would look like. This is a fifth order polynomial, this is a fourth order polynomial, this is a third order polynomial. And there is also one more scheme that is called a straight line interpolation with parabolic blends. So earlier we have seen about an interpolation between a start position and a goal position using just by a straight line, right? And we have also seen the consequences. Like if we simply join the initial and goal position to the straight line, the acceleration could have theoretically infinite infinite units in positive and negative directions at the beginning and the end of the trajectory. So in order for us to counter that, we can have some parabolic blends. So from time 0 to some specific value, we can have a parabolic blend. Then from here to somewhere around here, you can have a straight line. This is straight interpolation. And from this position all the way to the goal position, you can have again a parabolic blend. So that is what we have. We have with this parabolic blend, we incorporate some parabolic blends in between the initial and some time, some finite time. Let this be a TB time. This also be a time TB. And in between, we have a straight line interpolation. So since this is a straight line, what will the velocity look like? This is the first order. So the velocity would essentially be constant. And since this is a parabolic blend, this is second order. These are also second order. So if you take derivative of it, the velocity would be linear, straight lines. And if you again take the derivative of the velocity profile, you will have accelerations. So this would correspond to a constant acceleration that is labeled by this segment. And this would also correspond to a negative acceleration that corresponds to this segment. And constant velocity, this would correspond to zero acceleration. Velocity is constant. If you take a derivative, you will have zero. So this is how the profile of acceleration would look with parabolic blends. And we also have one more profile that is similar to, or that is exactly mimicking a cycloid, a motion of a cycloid. So as you all know, cycloid is the point traced by a point on the periphery of a circle as the circle rolls over a straight line. So if this is a straight line, and if this is the initial position of a point, so as the circle rolls without slipping, this point would trace something. This point would trace a profile, something like this, right? For a full rotation, it would start from here. It will go all the way from here, and it'll also reach the same position when the circle rotates one full rotation, right? So that is what we call a cycloidal motion. So what do we have? So the time basically varies from T0 to TF, right? So I'll just draw, this is time T0. This is our initial position, X0, time T0. And at another instant, it moves. It also rotates by an angle alpha. And this is the point at time xt, right? So what is this distance? What is this distance? What is the equation of this line? So essentially, we know this to be the arc length. This distance, this total distance is nothing but the arc length. That is, if I'm writing it here, this distance would be, arc length would be radius times the angle of rotation alpha, r alpha. And this point, this position would be r sine alpha. Then what would be this distance from initial position all the way to this position xt? This distance would be r alpha, sorry, this would be r alpha, x of t would be r alpha minus r sine alpha, right? So the equation of the equation of this point on this cycloid is nothing but r alpha minus r sine alpha. Okay, so we do some basic manipulation. So for this, for a full rotation, corresponding to 2 pi r, hang on one second. For a full rotation of 2 pi r, the Yeah, the distance traversed by the point would be xf minus x0, where x0 is the initial point and xf is the final point. Right? For full one rotation, it will be the distance covered by the point x would be 2 pi times r. And if you manipulate this expression, the radius would be xf minus x0 by 2 pi. Right? If this is x0 and at some time this is xf, the radius is nothing but xf minus x0 by 2 pi. And we also have a linear relation between this alpha, right? This is nothing but a linear relation. So alpha by 2 pi, these are angles. Alpha by 2 pi is proportional to T by TF, right? So the angle rotated at an instant of alpha would be proportional to the time. And if it rotates 2 pi radians, that would correspond to the final time of the trajectory. So alpha by 2 pi is T by TF. So in that regard, alpha would be 2 pi T by TF. Simple manipulation. So if you plug these values onto this basic equation, you would end up with something like this. This is what you end up with. I have also added an x0 because here in this derivation, I have considered x0 to be 0. But if you substitute these expressions for r and expression for alpha onto this equation, and if you add an initial time x0, this is your interpolation function, right? Cycloidal motion as a function of time. That is all this is about. And again, if you are interested, the profile of the position, the velocity, and acceleration would look something like this. More or less similar to a fifth order quintic polynomial. Right? Okay. Okay, so we'll also cover some schemes of motion planning. We can plan the trajectory or the motion planning in two variables, either in joint space schemes or either you could plan it in task space schemes. So each of these schemes has its own advantages, right? So what does each of them say? So in case of a joint space scheme, it says the type history of single or multiple actuated joints. So if you have a robot having multiple joints, theta 1, theta 2, theta 3. So joint space scheme basically deals with the type history of theta 1 of t, theta 1 dot of t, theta 1 double dot of t, and we have theta 2 of t, theta 2 dot of t, theta 2 double dot of t, all the way to the entire number of joints. You could either plan this in cubic or fifth order or cycloidal, whichever you feel fit, right? But when it comes to star space schemes, it is nothing but the time history of position and orientation of the end effector. So rather than theta 1, theta 2, theta 3, you would be planning the trajectory in terms of star space variables, which are x, y, z. Then you will also have the remaining parameters for rotational motions. Right? And the key specific features of task space is that they are more natural for a robot operator to specify. Because intuitively, if you want a robot to move from an initial position, if I am drawing a 2R robot, this is the end effector, initial position, and final position would be something like this. Yeah, so intuitively, if you want a robot to move from this position to this position, it is intuitive for us to define the trajectory between trajectory in terms of task space variables. Because if you want to move, we would mostly define the task or the job that a robotic arm that would be executing in terms of task space variables. So it will be natural for us to define the motion in task space variables. So this is more intuitive and more easier rather than specifying the trajectory in joint space, because it's easier to visualize and check for obstacles. And it may have some difficulty in orientation due to representation issues, because representing orientations is not as straightforward as controlling positions. You may end up in some trouble in controlling orientations because these are slightly coupled. So you can maybe control these independently, positions independently, but there will be some sort of coupling when orientation also comes into picture. So traditionally, two important task-based schemes are used for position. That is a linear interpolation and a circular interpolation. So in our course, we'll mostly deal with this linear interpolation, right? That is a straight line path between two given positions. And so what that essentially means is that, like, if we have an initial position defined by initial positions x0, y0, and z0, and we have a final position in terms of xf, yf, and zf. So a straight line interpolation essentially means that itself, like, it'll basically plan a straight line between the initial position and the final position, and the straight line essentially means it can have the time profile can be cubic, right? It does not mean it has to be a straight line. What we have seen here, maybe at time t is at 0, it can move somewhere here. At another instant, it can move this much. At another instant, it can move this much. At another instant, it can move this much. And when it is at the extreme, it will move in smaller increments, similar to how what we have seen for a cubic polygon. So what we do is that we first plan a trajectory, or we first come up with a trajectory in one variable, in whichever method you prefer. Maybe cubic polynomial, maybe x of t as a function of a0 plus a1t plus a2t square plus a3t cube, and the remaining polynomials would be, a straight line function of the first polynomial. For example, if we define x as a cubic polynomial, y can be made as a function of x. So y could be xf minus x0 by xf minus x0 by yf minus y0 times what is the general straight line equation? It is something like y minus y0 be y2 minus y1 by x2 minus x1 times x minus x0, something like this. So we already have x variables, right? We already have planned x in terms of cubic polynomial. So with this straight line interpolation, we can basically plan the y coordinates. And similarly, we can also plan the z coordinates. So z minus z0 would be z2 minus z1 by x2 minus x1, or multiplied by x minus x0. So if you plan it accordingly, the end effector would traverse from a straight line from the initial position all the way to the final position, right? So the first position, x, is basically a cubic polynomial, and y and z are basically straight line functions as a dependent, with the independent variable being x. Okay, so like earlier, we have seen the benefits of task-based trajectory planning. What are the benefits of task-based? Like it is agreed that they are more intuitive, because if you know an initial position of an end effector, if you know a final position of an end effector, these are basically easy to visualize in task-based. But what could be typical issues in task-based trajectory planning. It could be easier and it could be more intuitive, but there could be certain pitfalls in planning trajectories in task-based. So there are three such cases. We look at them one by one. So the first case is the task-based trajectory planning with non-reachable points. So this is an RR manipulator, a 2R serial manipulator, and the shaded region in gray depicts its workspace, right? So the lower circle, the smaller circle is basically when the arm is fully folded on itself. So if this is the first joint, right, and the second joint, if it is folded on itself, would come over here. This is the maximum it can reach. So it cannot go any further. It cannot go inside any further than this point. And if the arm is fully stretched, this is the first joint, this is the second joint. This circle is the maximum extent the arm can basically go. It cannot go any further than this. So this would be the workspace of this robot. So if you are given an initial position x0 and y0 and a goal position xf and yf, if you are planning this trajectory in task space, if you are using a straight line trajectory planning, what we have seen over here, if you are using a linear interpolation, your trajectory would look something like this. Your planned trajectory would look something like this using a linear interpolation. But obviously, you can see that the planned trajectory takes the robot outside its workspace. So the region here, this white region is basically outside its workspace, right? So the robot, the motion planning would essentially try to take the robot outside its workspace if you are planning this in task space. But instead, if you are finding the end effect, if you are finding the joint variables theta 1f and theta 2f, and you also have the initial joint variables theta 0, theta 10, and theta 20. And instead of planning a straight line interpolation in task space, if you are planning something in joint space, this situation would not happen. You know, instead of traveling something like a straight line in task space, the robot's end effector would execute a motion something like this, right? If you are looking on a different space, if this is theta 2 and if this axis is theta 1, right? You have initial theta 10, you have final theta 10, you have initial theta 2 over here, theta 2, you have a final theta 2 over here. So the trajectory in joint space is is also a linear interpolation, right? So the trajectory in theta 1, theta 2 space is again a straight line interpolation, but when it comes to task space, this entire coordinates is defined with respect to x and y, right? So this is x-axis, and if you consider this to be y-axis, if you plan a straight line interpolation in joint space in this coordinates, theta 1 and theta 2 coordinate, the end effector would execute something like this. It won't take it outside the workspace. It will execute a curve something like this. But if you are planning something in task space, it will try to cut through. It will try to go out of the workspace. So that is the peculiarity of trajectory planning using task space and joint space, right? So one example is the task space trajectory with non-reachable points. If you're planning it in task space, it may try to cut through. It may go beyond the workspace. And case 2, the task space with near singular points. So this is another example. So like as opposed to this case. So in this case, the 2R manipulator has unequal lengths. So this link length is larger than this link length. So because of that, you have a donut shaped workspace. But in case if both of these link lengths are of equal size, right? If the robot is fully extended, it can reach all the way up to this point. If the robot is fully folded, so this is the first link, it can also fully fold up to this. It can also reach at it. The end effector can also reach at this origin, right? So that is the case if you have an initial position and a goal position, as shown in this figure. And if you are again planning, if you are again using a straight line interpolation between this initial position and the final position, notice that it will also take you through the singular configuration. So singular configuration means like when both of the joints aligns, right? When this joint aligns with, when the second joint fully folds back on the first joint, that basically is a singular configuration of the robotic manipulator. So what we have already seen in the previous lecture that singularities are something that is to be avoided, because it will cause the actuators to have infinite velocities. So if you want to control a specific velocity, it can have theoretically infinite velocity. So that is something that is to be avoided. So if you are planning a trajectory, and if the straight line interpolation is forcing the robot to go through a singular location, this point is a singularity, then that is not good enough. It can have a lot of potential adverse implications, adverse effects. So that is one another aspect, task-based trajectory with near singular points. And the final thing, the case 3 would be possibilities of ending with other inverse kinematic solution. So again, if you plan a trajectory from this initial position all the way to the final position along this straight line, right? So as this robot moves from this initial position like this, so it will come like this, it will come like this, and eventually it will arrive at a singular configuration when the links are fully folded. And as it comes out of the singular position, it will come out something like this, right? So as you have already seen in the previous weeks, we have the 2R robot can have two solutions, two inverse kinematic solutions. So if this is the final position, X goal, Y goal, the 2R robot can have two inverse kinematic solutions. So the first solution being this, we call this to be the overarm configuration. And the second inverse kinematic solution would look something like this. Both of them are fully realizable. This is something called an underarm configuration. So here the robot basically starts with an overarm configuration, something like this, and it started something like this, and instead of ending up like this is how it should have ended up. If you are rotating it clockwise or counterclockwise, it basically ended up like this. So the robot can basically end up with a different inverse kinematic solution than what we desire. So if you want the robot to move in this configuration alone, because it is encountering a singularity over here, the robot is ending up with a different configuration. So that is what this means by possibilities of ending with other inverse kinematic solution. So these are the three possible cases that we have seen in the case of task-based trajectory planning. But if we had planned this straight line interpolation in joint space, then the robot would have basically ended up with this configuration. right? This position would rotate something like this. The end effector would assume a path something like this, and the final configuration would be like this. Instead of like this, it would have been like this if we had planned in joint space. Okay, so yeah, that's about it. The key theories that we came across week 6, and I would urge you to go through the lectures, especially the part where he discusses the trajectory planning of manipulators using MATLAB. That will basically give you more insights, so you will basically, it has some further additional information that is uh, that complements to what is being shared during the lectures. So yeah, now that we have the sufficient background for solving the questions, we can discuss some few questions that is relevant to the quizzes. You can expect similar questions during your week 6 assignments, right? So here goes. The first question, it says, these are all true or false questions, more or less. We have 10 questions. So the first question says, the specification of a robot position and orientation as a function of time is called path. It's a fairly straightforward question. We know that is not the case, right? We know the correct answer is specification of position and orientation as function of time. We call it as, the keyword is trajectory, right? Not path. So in that regard, the option is indeed false. So yeah, answer is indeed false. Moving on to question 2. It says, for a cubic trajectory planning, the acceleration profile may contain discontinuities across the wire points if wire point velocities are specified. So if you guys are still there, what are the answers? Would it be true or false? It says for the cubic trajectory, if the wire point velocities are specified, the acceleration profile may contain discontinuity. So yeah, I've got one response and it says to be true. And I agree with that. We have seen that, right? Yes, both of you have given the answer to be true. So I don't think there is any further need to clarify the answer. So that is indeed true. Okay, so this is a numerical question. It says for an initial joint position of 30 degrees and the final position of 60 degrees, right? If the initial and final velocities are 0 and the total trajectory is generated for 6 seconds, right? What will be the maximum velocity of the trajectory if a cubic polynomial is used? So how do we approach this problem? So we know that we are dealing with the cubic trajectory. We'll depict it somewhere over here, right? So we'll write it something like this. We'll draw something like this, sorry. A cubic trajectory. So we'll consider our initial time to be t0 to be 0, our final time tf. In the question, it is given as 6 seconds, right? Okay, yeah. Perimal Sami has given the answer to be 7.5 seconds. But can you explain how you got that answer? Is it possible? Our initial position is given as theta 0. Our final position is given as theta f. How did you get it to be 7.5? You can either solve with this analytically, you can solve this numerically. All sort of possible things are available. So I'll briefly explain the procedure. I guess the numerical answer is indeed 7.5. That is indeed the correct answer. 3 by 2 theta f. Yeah, that is the correct formula. Yes, but I'll just briefly give you the if you don't prefer to remember the formulas, if you don't like to remember formulas, just like in my case, I would do this quickly by hand. So we have this trajectory theta of t to be a0 plus a1t plus a2t square plus a3t cube, right? And the derivative of this theta dot of t is a1 plus 2a2 plus, sorry, 2a23 plus 3a3t square. So if you substitute this boundary condition, so initial position is 30 degrees at time t is t0. So 30 is a0 and initial velocity is 0. So if you substitute t as t0 onto this equation, sorry, if you substitute t as t0 onto this equation, you would end up with 0 as a1. And the final position is 60 degrees. So 60 would be a0 plus a1 times, final time is 6 seconds, a1 times 6 plus a2 times 6 square plus a3 times 6 cube. And the final velocity is 0. So that would be a1 plus 2a2 times 6 plus 3a3 times 6 square. So if you write this in the matrix and vector form, it will look something like this. You have a vector of unknowns to be a0, a1, a2, a3. Your boundary conditions are 30, 0, 60, 0. And this would end up with 1, 0, 0, 0. This will be 0, 1, 0, 0. And yes, the third equation would be 1, 6, 6 square, 6 cube. The fourth equation would be 0, 1, 2 into 6, 3 into 6 square. So you can use any method to find the inverse of this matrix. You can either use MATLAB, or if you don't have MATLAB, there is something called Octave. This is a free alternative to MATLAB. You can also have an online version of this. So for computations like this, if you search Octave in Google, you can have an online Octave or CTAVE. You can essentially get an online interface of Octave. You can plug in these metrics to find this inverse, right? Or you can also use your own calculator, because I believe calculators also supports finding inverse of 4x4 matrices. So if you consider this to be the matrix A, and if you consider this to be the vector B, if you take A inverse B, you would end up with the coefficients A0, A1, A2, A3. You will end up this with 30, 0, 2.5 minus 0.2778. Right? So A0 is 30, A1 is 0, A2 is 2.5, A3 is minus 0.2778. So the question is to ask, the question basically is asking you to find the maximum velocity, right? If the cubic polynomial is used. So if you substitute these coefficients, into the velocity equations, right? That would look something like A0 is 30, A1 is 0, A2 is plus 2.5 T. Sorry. Did I make a mistake? Yeah. So velocity equation does not have an A0 term. A1 term is 0 actually. Now what do we have? We only have A2. So velocity equation would be 2.5 times t minus, sorry, it'll be 2 times 2.5 t plus 3 times minus 0.2778 t square. This would be your velocity equation, right? And you are also asked to find the maximum velocity. And if you, I don't know if it's easy to figure out that the maximum velocity occurs at somewhere at exactly the midpoint of the total time, right? Because this is the position profile is constantly increasing. At some point, it starts, it encounters a point of inflection, and then it becomes a constantly decreasing function. So the velocity profile would look something like this: an inverted rainbow, or a convex, or a convex shape, and the maximum velocity exactly occurs at this middle point. So if the total time is 6 seconds, you can substitute the time, half of this time, 3 seconds, onto this equation. So if you substitute time t as 3 seconds onto this equation, you can find out the maximum velocity because it occurs at exactly the midpoint of the trajectory. And once you do that, you will end up with this equation. The correct way to do is that you also know that the velocity base is basically 0 at this point, at the midpoint. So you can basically take the derivative of velocity, dv by dt is equal to 0, and you can solve for t, and using that t you can back substitute it onto the velocity equation. That is the correct way, but this is also a shortcut because it is always going to be midpoint. It's always going to be tf by 2, where you will have the maximum velocity. So if you substitute whatever time you have been given, half of the time that you have been given onto the velocity equation, you will end up with the corresponding numerical value for the maximum velocity. So the answer is indeed 7.5 degrees per second. Okay. So moving on to question 4, what does it ask? It says a third order trajectory planner has control over initial and final acceleration. So is this true or is this false? That is indeed false, because a third order trajectory can have 4 boundary conditions. So it can only manipulate initial positions and velocities, as well as final positions and velocities. Okay, so I suppose there is no further need to clarify that any further. Okay, so this is something that you might have come across in the lectures. We'll read the question carefully. It says, if we define a variable u as t by tf, where u is an element from u is within 0 and 1, a closed interval of 0 and 1, then the cubic polynomial function can be rewritten in a nested form as. So we know the cubic polynomial to be a0 plus a1t plus a2t square plus a3t cube, right? And we have been also asked us to replace this by a variable t by tf. So it will be something like b0 plus b1u plus b2u square plus b3u cube. And the reason that we are doing this is that we are basically scaling the time from 0 all the way to tf to 0 to 1. And why are we doing this? The reason is that, like, if you can recall, if you solve this equation, the equation of the cubic polynomial, the coefficients a0, a1, a2, a3, some of the coefficients have denominators time TF cube or something like TF square. It will have denominators in TF. And if the TF is too large, right? If the TF is too large, then some of the coefficients A2 or A3, it may tend to 0 if TF is very large. So in order for us to avoid that case, we would scale the time varying from T to TF between 0 to 1. And because that we are using a change of variable, our new equation would look something like this. And we can write this equation in a nested form. Yeah, numerical instability. We can also use this in a nested form. That is something like B0 plus, if I take this U as common factor, it will be like B1 plus, again, if I'm taking U as a common factor, it would be B2 plus UB3. Because this is much more efficient. This has 3 additions, right? 1 addition, 2 addition, 3 addition. And it will only have 3 multiplications, 1, 2, and 3. This is also more computationally efficient than using the previous method. If you are time scaling, this would be more efficient, and this could also be more numerically stable. So yeah, we are simply rewriting this cubic polynomial into this nested form. It's a simple mathematical manipulation. It's a fairly straightforward question, and the correct answer is indeed option 5. Yes, I've got an answer as option 5. That is indeed correct. Because if you expand this, you will again end up with the cubic polynomial. That's all the question is about. Yes, the option is indeed option 5. Okay, so moving on to question 6. So this is also a similar question that we have. Okay, I have got another question. If there are more time intervals between 0 and 1, then will the new form will have accuracy issues? I don't understand the question. If there are more time intervals between 0 and 1, what do you mean by that? 0 and 1. No, because in that case, TF is essentially 1, right? So no matter how large your TF is, it will eventually scale it onto 1. So like earlier, you have coefficients TF cube or TF raised to square or something like that. So imagine if you have TF to be around 10 seconds or something. So TF cube would be 1000, TF square would be 100. Yeah, exactly. And if your numerator is very small, the coefficient would be because of this term, because of these terms, due to the fact that we have TF cube and TF square, the terms that contains TF cube and TF square would tend to 0. But if you're scaling, if you are using this substitution, U as T by TF, so it does not matter if whatever be the time TF, however large it be, it will eventually scale back to 0 and 1. Right? It will eventually scale back to 0 and 1. So you further won't be having any further issues. You won't be having any further issues because now your TF is essentially 1. Your new TF would, after the scaling, is essentially 1. So you won't be having any more further issues. After the scaling, yes. Okay, so I'm getting more chat. So instead of, because of, okay, can you clarify? Can you come on, use your microphone if that is possible? I'm not following what your question is. Would it be possible? Okay, we can do this later, yeah. But I hope this is clear enough, because if you are using if you are not scaling, or if you are not using this substitution, and if your TF is actually very large, and if you are not using this substitution, some of the terms, some of the coefficients would tend to be very small. And if you are using some round off, it will be close to zero, and it can basically lead to some erroneous coefficients, and you won't be able to get the desired trajectory. But if you are using the substitution, so no matter how large your time period is, it will eventually scale back to 0 and 1. So yeah, you won't have any further issues, because once you do that, your final time is essentially, you would be scaling back to UDT. Okay, so moving on to question 6. So this is also similar to the problem that we have seen. So instead of the velocities, they are simply asking us to find the trajectory, or the interpolation formula. So the question basically gives you the initial position, theta 0 to be 20 degrees, and the final position, theta final to be 60 degrees, and the time at which it takes from moving 20 degrees to 60 degrees, it is given as 10 seconds. 10 seconds. And we are also supposed to plan the trajectory using a third order polynomial. Okay, again, I've got the option as 0.5. Let me check if that is the correct answer. Yes, I suppose that is indeed the answer, option 5. But again, I suppose you all already know the correct answer. The matrix expression would look something like this: 1 0 0 0 0 1 0 0, then 1 TF, TF square, TF cube, 0 1 2 TF, 3 TF square, and you have the coefficients A0, A1, A2, A3, and you have the boundary conditions as initial position to be 0, initial 20, initial velocities to be 0, because it's given in the question as the initial and final velocities are 0, and the final position is 60 degrees, and the final velocity is also 0. This is your A matrix, and this is the B matrix. And if you want to find out the coefficients A0, A1, A2, and A3, you only need to take this inverse, A inverse times B. If you evaluate this expression, if you evaluate this matrix manipulation, you will end up with a vector that corresponds to A0, A1, A2, and A3. Right? So if you do that, the answer is indeed going to be option E, or the fifth option. Okay, you could use MATLAB or Octave or even your scientific calculator. They have the capabilities to perform 4x4 matrix inverses. So the answer is indeed option 5. Okay, moving on to question 7. It's also a straightforward question. A fourth order trajectory planning can satisfy initial and final constraints of position, velocity, and accelerations. So can a fourth order polynomial satisfy 6 constraints? It cannot. Yes, that is indeed the answer. We have discussed why that could be the reason. Because a fourth order polynomial can at most satisfy 5 constraints. It cannot satisfy 6 constraints. Right? Only a fifth order polynomial can satisfy 6 constraints. Okay, so I suppose there's no further need to clarify that. Okay, so moving on to question 8. This is also a trajectory question. So it says for a single rotary link manipulator, the initial position is 20 degrees. So x0 is 20 degrees. And the final joint position is 60 degrees. So xf or theta f, whichever notation you prefer, is 60 degrees. And the final, the time taken for the trajectory is tf is 10 seconds. Right? And the motion is supposed to be a cycloidal motion. Then what will be the maximum joint velocity? I have obtained the option as option 1, 6, radians per 6 degrees per second. Let us see whether that is the case. So I hope you can recall the equation of the this equation for the cycloid is r alpha minus r sin alpha, right? So if you substitute the right values, x of t is nothing but some x0 plus xf minus x0 by 2 pi, the whole multiplied by 2 pi t by tf, that is your alpha, minus sine alpha would become sine 2 pi t by tf. So in order for you to find out the velocities, you will have to take the derivative of this equation with respect to time. So what would that be? It will be xf, velocities x dot of t would be xf minus x0 by 2 pi. It will be 2 pi by tf, then minus xf minus x0 by 2 pi. And if you are taking the derivative of sine 2 pi t by tf, it will be cos 2 pi t by tf, the whole multiplied by 2 pi by tf, right? So what will happen? So 2 pi and 2 pi will get cancelled. Here also 2 pi and 2 pi will get cancelled. So taking out the common terms, which are xf minus x0 by tf, we also have the common term over here. So xf minus x0 by tf as common, we have 1 minus cos 2 pi t by tf. This would be your velocity, x dot of t. So if you plug onto the values that you have been given onto the question, what will you get? So xf is 60, x0 is 20, tf is 10. Then on the brackets you have 1 minus cos 2 pi. So again, it is asking you the velocity. Yes, it is asking you the maximum velocity, right? So again, we know the maximum velocity happens halfway the trajectory, halfway of the trajectory, right? So yes, halfway of 10 seconds would be 5 seconds. So t would be 2 pi into 5, then you will have 10 seconds. So cos 10 pi by 10 is cos of pi, right? So if you simplify this again, 60 minus 20, this is 40 by 10, 1 minus cos pi. Cos pi is minus 1, right? So this will be again 40 by 10 times 2, I guess. So this will be 8 degrees per second. That will be the answer. Yeah, so the answer is indeed 8. Yes. Okay, I think you have changed your answer to 8 radians per second. So that is indeed the correct answer. 8 radians per second. Yes, that is indeed the correct answer. So like it's the problems are all fairly straightforward. It's only a matter of plugging in values what you are given in the question into these equations, right? Okay. The ninth question is, in a 2D space, if xt is generated on us, is xt is generated based on one of the smooth trajectory generation schemes, then what will be y of t based on a straight line interpolation? So you basically have an initial position x0, y0 in a plane. You also have a final position xf, yf, and you want to have a straight line interpolation between this initial and final positions. This is a straight line. And you are also given that you would be planning one of the coordinates xt. You are planning on one of the smooth trajectory schemes. It could be a third order, or it could be a fifth order. It could be cycloidal, anything, or it could be a straight line interpolation with parabolic blends. It does not matter. If you have already planned for one of the variable, and if you want the trajectory to be a straight line interpolation, how would you plan the remaining variable? How would you plan the y variable? So this is also again nothing but a straight line interpolation. So here you can take the independent variable to be x and the dependent variable to be y. So again, if you simply write down this equation of line, what would be the case? So you know the straight line equation of the line y minus y0 or y minus y final would be y final minus y0 by x final minus x0 whole multiplied by x minus x final, right? These are different variants. You could also write it as y minus y0 is nothing but yf minus y0 by xf minus x0, x minus x0. Right? These are all valid equations of straight line. Right? And which of this option is correct corresponding to the given options? If you take this y0 over to this other side, I guess everything is given with respect to yf, right? So if you take this yf to this other side, I think the correct answer is x minus xf plus yf. So I guess option B is the correct answer. Disregard. Yes, option B. Okay, that is indeed the correct answer. So moving on to the final question. It says the best trajectory between 2 points is based on straight line interpolation, that is constant velocity motion in terms of smoothness. Is it true or false? So if you have one point, if you have another point, in linear direction, if you are saying, if it is saying that this is how you are moving, right? Based on a straight line, this is the profile position, profile. This is T0, this is TF. And if you take the derivative, the velocity would be constant. Velocity profile. Because that's what the question says, right? Constant velocity motion. And what does the question ask? It's a true or false question. It says the best trajectory between 2 points is based on a straight line interpolation in terms of smoothness. Is this smooth enough? If the velocity is a straight line or a constant velocity, as we have already seen, the acceleration would be infinite at t0 and infinite at tf, while being 0 between tf and t0. So you can confidently say that the straight line interpolation is definitely not the best trajectory in terms of smoothness. It's definitely not the best trajectory. So the answer is indeed false. Option 2 false, yes. Okay, so that is again the correct answer. So yeah, so with that, we wind up the topics on trajectory planning or motion planning. I would also urge you to go through the MATLAB codes, because that will give you a real feel of how to plan the trajectory of a robot manipulator. Because throughout this discussions, we have only taken care of a single variable. Right? We have only taken care of x0 as a variable or theta 0 as a variable. But if you want to control an entire manipulator consisting of different multiple joint variables or multiple task space variables, how to do that? Right? So if you want to get that intuition, I would recommend you to go through the videos that is being posted by Dr. Shantakumar. Okay, so yeah, with that, we wind up the session on motion planning. Next week, we'll discuss the topics regarding motion control. right? So that will be the second last week for week 7. So until then, see you. Thank you for joining. So bye. See you next week. Thank you. Unless you have any further questions, you can log off. Oh, thank you. Okay. Okay, I'm ending the session. Thank you.